Good evening and greetings once again, minions. As per usual, I am Nathan. I'm a chemistry PhD student, a few months away from graduating, God, I hope. And I just felt like that wasn't enough chemistry, so I decided I would be the biggest nerd I know and take my free time to do this as well. So, that said, I was trying to think of if I've got anything else to talk about. Because there was a couple headlines that I read. Really, not. I confess I did not read the full articles, although I made note of them to go back and research a little bit more about it. Super didn't do that yet, but it is still written down somewhere, so I probably won't forget forever. But it was mostly concerning some really neat advancements in nuclear fusion technology, where they suspect that they've found a viable breeding reaction for tritium, which is otherwise extremely hard to come by, and is very necessary for the types of fusion reactions that we do. Because in fusion, we're fusing generally deuterium and tritium. These are both isotopes of hydrogen, just with different numbers of neutrons. So hydrogen, the vanilla type hydrogen that we know and love, has a nucleus consisting of one proton. Deuterium has a nucleus of a proton and a neutron, and is not very common. It's about 0.1% of the natural abundance of hydrogen is in deuterium. I think that's about right. And so it's pretty scarce, but it can be separated out and concentrated, and it is a stable isotope, which is important because tritium, which is a proton and two neutrons, is quite radioactive. I don't recall off the top of my head the half-life of tritium, but it's somewhere in the days to weeks range, I believe. But who am I kidding? I'm on a computer. I have access to Google. I can look this up. Tritium half-life. Oh, I'm completely wrong. 12.3 years is a tritium half-life, which still is highly radioactive and leads to this being an essentially 0% abundance of the hydrogen isotopes that we have access to, and is not counted in the natural abundance of hydrogen. Like 12.3 years is a pretty mediocre half-life. It's quite short, really, when you consider things like uranium 238 has a half-life of several billion years. Hello, my prayer. I'm sorry, I turned off your water thing. It's very loud. You can go get your other, though. Yeah. Thank you. But anyways, yeah, so we, so the thing with tritium is we don't have any particularly effective ways to make it, at least not that I'm aware of, because you have to essentially get a have to have a breakdown product that includes tritium with it, because it's awfully hard to just get, like take a bunch of hydrogen and shoot neutrons at it and hope they stick, and hoping that two of them stick, because you can't just do that with deuterium. But at any rate, that, as I said, is something I did not look up, although I had meant to, and I will do that at some point. And then I will spend a bunch of time talking about it, because yeah, it's quite neat. Like basically my takeaway from all this is that the pace of our technological advancement towards viable fusion energy is pretty much breakneck as far as these things tend to go, and so it's the running joke for a very long time was that fusion energy is 30 years away and always will be. Uh, but that no longer appears to be the case. Viable fusion energy is almost certainly less than 30 years away, and I would hazard a guess that it is less than 20 years away from scalable production of it. Anyways, that's enough. Just aimless, meandering technobabble. So I have, as always, a problem set to work on, and we will get to that presently. But as always, this is intended to be a responsive tutoring stream. So if there's anything that you want to talk about, any types of problems that you want to do, kind of preferably chemistry related, but not at all necessarily, because I'm ADHD as hell. I like talking about a lot of things, and we will rabbit trail just as often as I'm inclined to, which is a lot. So, without further ado, the first question here is talking about identify the nucleophilic centers in each of the following compounds. Now, nucleophilic being one of a pair, so there's nucleophiles and there's electrophiles in this kind of category, and so nucleophiles are molecules, atoms, portions of molecules that have a high concentration of electron density. So at least one area on the molecule at least has this kind of enhanced electron density around it, and electrophiles are the opposite. It can be a portion of a molecule or an entire molecule or just an atom that is in one way or another deficient in electrons. It has at least a region of low electron density, and as with 98% of all chemistry, the entire point of it is to spread out the electron density as much as possible, to level out these areas of high concentration and low concentration of electrons. So nucleophiles are regions of high electron density, and okay. But I should say that's not all that nucleophiles are, because something could have a high concentration of electron density and be non-nucleophilic or close to it, because kind of rolled into the definition of a nucleophile is the ability to share these electrons. And so when you have, for example, okay, so if we have a molecule of methanol, and so if we take that and mix it with a strong base, we can deprotonate the methanol. This ends up with an extra lone pair on the oxygen and a negative charge on that oxygen, and so that is a region of high electron density. And so this is just methoxide, and methoxide is, first of all, a very strong base, and also a very powerful nucleophile. Not on the extreme end of either of these categories, but strong base and strong nucleophile. And those two characteristics going together is not merely by coincidence. The things that make something a good nucleophile are very frequently the same things that make it a good base. So there's a lot of commonality in those properties, but they are different. Let me show you a case in which they are different. So if we have a similar molecule, but this time each of these hydrogen atoms is going to be replaced with a methyl group like that. Okay, so up here we've got methoxide, which is essentially just an oxide with a methyl group on it. This molecule is tert butoxide. Whoops, that is not how we write a T. Ooh, forgive my penmanship today. That was atrocious. My mouse sensitivity was very. Give me a moment. Okay, that's fine. We'll leave it as. So this is a molecule of tert butoxide, and so both of these are strong bases, and tert butoxide is in fact an even stronger base than methoxide, which I should write up here. Okay, so this is methoxide, this is tert butoxide. So this is a stronger. I don't know what I did there. There we go. All right, so tert butoxide is the stronger base. Oh God, why can't I appear to be unable to write legibly today. So I'll just write out for methoxide. Methoxide is a good base and is a good nucleophile. There we go. Tert butoxide is a stronger base. It is a very, very strong base, in fact. But it is a very poor nucleophile. And so the reason for that is that this T-butoxide, it is a very strong base, even stronger than methoxide, because this electron density is somewhat higher than this electron density. However, it's not obvious at all from the Lewis structure that I've drawn here, but this oxygen, this nucleophilic site, is very sterically crowded, which say like all these methyl groups and all that are the electron clouds of those methyl groups hinder the access that anything else would have to that oxygen. So they physically get in the way of anything that oxide would like to react with. Kind of rolled into this definition of a nucleophile is the ability of a potential nucleophile to share its electrons, and this is a very poor one because this oxygen it finds it very difficult to reach an electrophilic site because it's just so crowded by all these other methyl groups around it. And again, you can't really see that from the Lewis structure, but in a three-dimensional model, it's called a space-filling model that just kind of gives an approximation of like how big the electron clouds of these different groups are. If you do, make one of those, then you can see fairly clearly that it's very difficult. Like something would have to be oriented in just the right way to bump into the tert butoxide, and it would have to be like pretty accessible itself. If it's a really hindered electrophilic site, an electrophilic site that is also crowded out by big groups around it, then they simply won't react at all. Because this is the thing in chemistry, is it can look great on paper, but really what we're talking about when we say things react with each other is that and most often in a solution, in a liquid form, you've got all these molecules bumping around into each other, and the things that react together, they have to be close to each other. They have to be oriented in a way that the reactive sites can react with each other, and they need to have enough energy to react. They have to be at a another way to say that is they have to have a sufficient be at a sufficient temperature in order to overcome some of the electrostatic repulsion that they'll feel. And kind of get to the good stuff, as it were. That was a weird way to say that, but we're just going to go on. So, as a very brief rundown on what nucleophiles are, and so we'll go through these and we'll identify those, and then we'll talk a little bit about electrophiles. So first thing I'm going to do is I am going to add lone pairs to the appropriate sites. That is oxygens, nitrogens, other oxygens, any halogens will have lone pairs. And that's kind of all that you can count on for sure, having lone pairs, but it's a good start. So, nucleophilic centers are, well, first of all, this oxygen. Now, with the methoxide, it became a good nucleophile when we removed a proton from it, so that it could have another lone pair, another 2 electrons around it, and that's what made this a good nucleophile. And an oxygen with 2 single bonds, or 2 bonds and 2 lone pairs, it will be less nucleophilic than an oxygen with 1 bond and 3 lone pairs, because its electrons are more spread out. You could say like the 2 quote unquote extra electrons that this one has are tied up in this bond between oxygen and hydrogen, and so these electrons are more spread out. So it's not as good of a nucleophile, but it is still a nucleophile. You can still do stuff with these lone pairs. And so the other nucleophile on this compound is the pi bond. So not the sigma bond. So there's 2 bonds here. It's a double bond. And whenever there's a single bond, like any bond at all, the first bond that forms is going to be a sigma bond, which is something I don't feel particularly like explaining fully what that is right now, because that I could very well take 30-40 minutes to go over what makes sigma bonds and pi bonds. But suffice to say, it is like none of these bonds are nucleophilic, because there's only one of them. This is all that holds these atoms together, and so there's going to be exceptions to this. But when it's between carbons, a single bond is not a nucleophile, and so just frankly, just don't use it for anything. It takes particular conditions to get carbon-carbon single bonds to rearrange at all. Not true of double bonds, and specifically the second bond of a double bond, which I will at the moment just call a pi bond without explaining that further, because again that's for some other time. So the pi bond, which is the second bond here, can also be used as a nucleophile. Went over this a little bit last week with one of the reaction mechanisms that we were drawing out. We used it as a nucleophile to attack a halogen, which they're quite good at. There's a lot of chemistry that we can do with double bonds or alkenes, as these would also be correctly called. So yeah, those qualify for as nucleophiles. In this molecule, there's really just two nucleophiles, and they are the nitrogens. And one big giveaway for nucleophiles is just the presence of lone pairs. Most things with a lone pair can be used as a nucleophile. Because it's essentially just electrons that are sitting around, not really doing anything, and so they usually can be convinced to go and react with stuff. Now, the better nucleophile is this one, because this is a tertiary amine, which means that it is a nitrogen that has bonds to 3 carbons. Whereas this one is a primary amine, which means that it is connected to 1 carbon. The other 2 atoms connected to this nitrogen are hydrogens. And tertiary amines have somewhat higher electron density than primary amines. The more carbon groups you add around nitrogens, as opposed to hydrogens, the more carbon groups you have, the more electron density you'll have, because hydrogens do not have any appreciable electron density. They have exactly 1 electron, and that is tied up in the bond. Okay, so this molecule, this one is a little bit trickier, but the nucleophilic center on this molecule is the carbon right in the center, and that is because of the lithium. And so this is called an alkyl lithium compound, I guess. Really, it would be lithium T or tert butoxide, just referring to the arrangement of the 4 carbons that are attached here. But this carbon is a nucleophile, despite having no charge on it. It at least appears to be a neutral carbon atom. So it has no charge, and it has no lone pairs, sort of. So here's what I mean by that. What it does have is it has a partial negative charge, because carbon and lithium have a very large difference in electronegativity, which is just how hard they pull on the electrons around them. So lithium has a very low electronegativity, and carbon has not a high electronegativity, but a significantly higher one than lithium. And so the carbon here is pulling on the electrons in this carbon-lithium bond significantly harder than the lithium is. So this creates an excess of electron density close to the carbon and a deficiency of electron density around the lithium. And essentially what these are, or I should say, another way that you can represent alkyl lithium reagents is here. Here's what I do when I can't decide how I'm going to draw a thing. So another way that you could represent this is like this. Now, the the electronegativity difference between carbon and lithium is not enough for the carbon to completely kind of like steal the electron from lithium, because this would be an ionic compound, so an ionically bonded compound, whereas this is written as a covalently bonded compound. But this is like in a reaction where you're using an alkylithium reagent, you can get a very good approximation of what will be happening in solution by writing it like this, with the bond breaking and all of the electrons going to carbon. It is essentially a source of C minus, this carbon with a negative charge on it. And this negatively charged carbon, of course, is very nucleophilic. It's an extremely strong base and an extremely good nucleophile, because carbons with lone pairs are ridiculously reactive, and in this case they're reactive because they are extremely strong nucleophiles. Okay, and so this compound now, if we were to draw it out like this, cheeses of cakes, it's lovely to see you. I hope you're doing well. All right. So fully drawn out, at least as this is written, it would look like this, with the sodium bonded to the oxygen to the hydrogen. But that is not at all the reality of what this molecule is. Now, unlike in an alkylithium reagent, the electronegativity difference between sodium and oxygen is enough to fully to fully polarize that bond towards oxygen, which is to say that the electron that sodium uses to create a bond is entirely stolen by the oxygen, because the oxygen just pulls so much harder on the electrons that it fully separates it from the sodium. And because of that, now we've got an oxygen with 3 lone pairs and a negative charge, and that is a good nucleophile. Sodium hydroxide also being a strong base. Again, this is not a coincidence, because nucleophiles and bases contain a lot of the same criteria. All right, and contrasting that with electrophiles. So nucleophiles are areas in a molecule with enhanced electron density, or high levels of electron density. And electrophiles are the inverse. Are nucleophiles electrophiles, meaning things that are adhesive to electricity or nuclei? Sort of. Nucleophile and electrophile are actually quite archaic names for what these are, because there's a fair bit of nuance as to what is actually happening from a chemical perspective. But the terminology of nucleophiles and electrophiles has kind of remained where it has been for the last 100 years or so, and it is most certainly due for an update, because there's certain things that can look like they should be nucleophiles by certain definitions but aren't, and vice versa. But if you break it down to essentially what is meant by nucleophile and electrophile, then like you can kind of use the terms and not worry about it too terribly much. So just be aware that there is nuance. But for now, suffice it to say that nucleophiles are regions of a molecule with with a high electron density, and electrophiles are regions of a molecule with low electron density. And then these come together, of course, to spread out the electron density, which is 98% of all of chemistry. It's all just about reducing electron-electron repulsion. So if we're going to look at, like, to identify the electrophilic centers in these compounds, which mostly are different. So things that you look for in electrophiles are either positive charges, which indicates a deficiency of electrons, or partial positive charges. And when I say partial positive charges, I mean that when you look at a bond between two atoms, you can compare the electronegativity of those two atoms, and that will give a measure of how polarized that bond is, which is to say, the extent to which the electrons are kind of focused on one of the atoms and not the other. So in this example, where we've got an oxygen bonded to a hydrogen, for example, oxygen is one of the most electronegative elements on the periodic table. So it pulls very hard on the electrons in the bonds around it. Hydrogen has quite a low electronegativity. Certainly not the lowest, but it's not high. So that means that in this bond between oxygen and hydrogen, the electrons are going to be much closer to the oxygen because the oxygen is more electronegative. So there will be a partial negative charge on the oxygen and a partial positive charge on the hydrogen. And so this hydrogen will be an electrophilic center in the compound, but also this carbon, because carbon has a very similar electronegativity to hydrogen. It's a little bit higher, but not by much. And so this carbon also will have a partial positive charge, and so that is a electrophile as well. And in the case above, when we were looking for nucleophiles, it was the oxygen and that alkene, the double bond of that alkene. But that's not just because it was a nucleophile here doesn't mean it has any kind of a decent electrophile here. Because these are all carbons that we're talking about, so there's no partial positive charges that we can really invoke for these carbons. So I would say the only electrophilic centers on this molecule are the carbon and the hydrogen. So with this one, to think for a moment. Would that make it? I'm going to leave that one for a minute. There's something to think about in there. Let's go to this compound. So this has an iodine attached to a carbon chain. All the carbon-carbon bonds are non-polar, so those have no enhancement or deficiency of electron density, and all the carbon-hydrogen bonds are effectively non-polar because the electronegativities are very close. So there's no partial positive, partial negative, or a very, very small amount that does not qualify it to be an electrophile. Because you would if you were to call the hydrogens here electrophiles, you would lose marks on any exam that I've ever sat or invigilated. However, over here, so largely what we're looking for is just look for two different types of atoms that are bonded. Carbon hydrogen, very close in electronegativity. That ain't it. But carbon and iodine have a fairly significant difference in electronegativity, enough that you would call this iodine partially negative and the carbon partially positive. And so your electrophile or your electrophilic center is here, and that is the only one. Now, so in this molecule, so we've got a few different electrophilic centers on this molecule here, and first one is reasonably obvious. It is the carbon bonded to the oxygen. Again, oxygen is very electronegative. That has not changed since the last example. So it has a partial negative charge, and it is double bonded to this carbon. And the fact that there's two bonds between the oxygen and the carbon enhances it makes the partial charges associated with that bond bigger. So this carbon has a significant partial positive charge on it. And you can also demonstrate that in drawing out resonance structures for these compounds. So one resonance structure we can draw is here. So we got, if we take this double bond, break the second bond, and put the electrons up on oxygen. That gives the oxygen a negative charge, and so on and so forth. I don't care about that part. But what this does is it gives this carbon a fully positive charge. This is a carbon with 6 electrons around it. It is deeply unhappy with that situation, but this makes it a fantastic nucleophile. That's the wrong set of words. I'm sorry, English is hard sometimes. In my defense, I'm very stupid. But this carbon has a deficiency of electrons, which makes it an electrophile. It wants electrons. And carbons that are part of a carbon-oxygen double bond are some of the most common functional groups that we use in it's like reaction mechanisms, and a metric crap ton of synthetic chemistry is based around the chemistry that you can do with carbonyl groups like this. A carbonyl group just being some place where you have this carbon-oxygen double bond in. So this is an electrophilic center. This one is also, because this is the exact same situation. We have a carbon double bonded to an oxygen. Now, the reason that I needed a moment to think about this is that I think there's a good argument to be made that there are additional electrophilic centers here, and that is the hydrogens that are attached to the carbon next to the carbonyl, and so that would include these ones and these ones as well. And here's why. Okay, so if you have, let's put this over here so it's not behind my face. So if you have some kind of a base, so it's just B for just a base, something, and this does take a reasonably strong base, because carbon-hydrogen bonds are not super easy to break. In fact, they can be really quite difficult to break. But it can happen, and we use situations like this to do a lot of that kind of chemistry. So if a base were to come in here, the hydrogens that it would attack first would be these ones. Just one of these two. It makes no difference which one. These hydrogens have exactly the same ability to be attacked, I guess. You could call it this. They have the same acidity, or pKa. So if a base comes in and attacks this hydrogen, it deprotonates the carbon, because this arrow represents the base forming a bond with a hydrogen, and hydrogen can only support one bond at a time, right? Because it's only got that one s orbital, so it can only tolerate 2 electrons around it. So once you form a bond to the hydrogen with the base, the other bond has to break. And so we can put the electrons from that reaction onto the carbon. Let's do this. Okay, so this has still the hydrogen, and now it's got a lone pair and a negative charge. Excuse me. But now normally we would not do this, as it takes a almost unthinkably powerful base to deprotonate a carbon, usually, but not in this case. In this case, we can do it with some pretty accessible bases, things like sodium hydroxide, which is extremely common. The reason that we can do this is because this negative charge is stabilized by resonance, because you can use this lone pair to form a double bond between this carbon and this carbon, and when you do that, okay, so I did not draw an H here. It is implicit in the line structure, because all the carbons are assumed to have 4 bonds at all times. So when we form the double bond here, we must break one of the bonds around this carbon, because carbons can only support 4 bonds, right? Because in its valence shell, it's got the 2s and the 2p orbitals, which have 2 and 6 electrons. So the carbon can only support 8 electrons, 2 in each bond, 1, 2, 3, 4. So if we form another bond, we have to break one of these bonds, and we're not going to break the carbon-hydrogen bond. That would be extraordinary. So usually we don't like to do extraordinary things. If you have to do something extraordinary in a mechanism, it's probably wrong. But what we can do is we can break one of these bonds to the oxygen, and we can push those electrons up onto the oxygen, and it'll become a lone pair. Double bond. Okay. That's got the negative charge. So by doing this, we have moved the negative charge up to the oxygen, and carbons are extremely unhappy with a negative charge, and most of the reason for this is that carbons have a low electronegativity. And so things with high electronegativity, like an oxygen, they are pretty okay with bearing a negative charge. And remind me at some point, talking to myself mostly, because I should be doing the reminding of myself. At some point, I do want to talk about like what electronegativity is and why we can do things like this. But for now, I'm not going to, because I don't feel like it. So, but because we had that bond here that we can break, oh, I suppose more or less on the spot. Like this is definitely something like I could just launch into an explanation of it, but we might be here for another like half hour if I were to do that and spending good time just on this. And I do want to get a little bit into some more orbital theory with you today. But yeah, at some point, I certainly would like to get into that discussion. Orbitals were always orbitals are just the best. They're so good. Yeah, like really, like one of the best ways that we have to represent what chemistry does, and a great way to rationalize the observations that we make and make very solid predictions, which is really what you want to see out of scientific theory. So it's great. Yeah. So because we had a bond here that could break, and an atom that could bear that negative charge, now we've spread this negative charge out between two different atoms. And again, as always, most of what we're trying to do in chemistry is reduce electron-electron repulsion, to spread out these areas of high electron density. And that's what this resonance structure does. And this resonance structure, the ability to form this resonance structure, is why these hydrogens are relatively acidic, which say they can be removed from the carbon because that negative charge can be spread out. Like, and for example, you super duper could not do the same thing with one of these hydrogens, because let me redraw the molecule as it was. 4, 5, 6. I know that's behind my face. I'll move it in a minute. Okay, so if we were talking about these hydrogens. Okay, so if we had another base here, we could. So we can form a bond with this hydrogen and put the electrons onto this carbon, and that produces, oh, and that's an H, of course. Ugh. Yeah. Okay, so this is what we would get from that reaction. And okay, so now this negative charge, it's very similar to the one that we formed above, but there's a very important difference, which is that we cannot draw any resonance structures that spread this charge out. because the only possible things that we could do with this lone pair is we could form a double bond on either side. It could be going here or it could be going there. But that's where we have that's where we run into problems, because this carbon has 1, 2, 3, 4 bonds around it already, and so if we were to form a double bond here, we have to break one of these bonds around it. And there's no good options. There's no double bond that we can break, and just put another lone pair around something. We could, on paper, very important that here it is, we could on paper break one of these bonds to hydrogen, and that would produce. I'm just going to. No, I'll draw out the whole thing. That. Okay, so this is the molecule that we would form from this reaction. And that kind of looks okay, right? Like this doesn't look too bad at all. But that is not the only thing that would form from this reaction. We would also have a hydrogen with a lone pair on it and a negative charge, and this is called a hydride. And this is something that we don't do. We don't just like kick a hydrogen off of a molecule and form an H minus like this, because it's extremely unfavorable. Because an H minus is very, very unstable, and extremely reactive. And if by some miracle bestowed by the chemistry gods, you got this reaction to move forward, to actually undergo this and kick off the H minus, you would immediately, practically instantaneously, see the hydride coming back and attacking that one of these carbons. It doesn't actually, it does matter which. It'd be this one. Don't worry. So it would immediately attack this carbon, and that would again, you can only have 4 bonds around a carbon at any time. So we have to break one of these bonds, and by far the best one to break is the second bond here, the pi bond, and that would put the lone pair back on this carbon, and this would essentially go straight back to that product. Now, and that is me giving every benefit of the doubt that you could do this at all, but you can't. It won't happen. This is like kicking out an H minus, like breaking this bond is so extremely unfavorable that you wouldn't see this happen at all. And because that's the case, because effectively this minus charge will be stuck on this carbon, and there's no stabilization for it at all. There's no really electronegative atoms that are close to the carbon that would draw electron density away and kind of counteract that negative charge. There's nothing like that, and there are no resonance structures that we can draw. So this is an unstabilized charge on the carbon, and because of that, in fact, this step won't happen either, because these are extremely non-acidic hydrogens. It is extraordinarily difficult to remove those from the carbon. Sorry, I keep looking out the window because I just got a notification that we're under a severe thunderstorm watch, and it's looking a little spicy out there. If that is okay, we'll go on for a little while. If I suddenly disappear, though, it probably had an interruption of power, so don't worry too much about it. Anyway, okay. So I think. Yeah. No, I do suspect that like mostly anywhere in the States would like have just worse thunderstorms than we do up here. But yeah, like it definitely could get a little spicy. We do have we do occasionally have tornadoes in Alberta. Although it's not in living memory that that there would have been one here where I am, but yeah, we'll see what happens. Oh, there was so all of our pets now, the Callisto the dog and Persephone and Daphne the catos, none of them are particularly bothered by thunder and lightning and all that stuff. But the last pup that we had, Achilles, he was such a good boy, especially good of most storms can be like hurricanes. Yeah, I know. Like that's when it gets real dicey. But yeah, no, I honestly, like in Alberta, like natural disasters are they don't happen all that much, but yeah, it gets damn cold. That's all you can say. Like, blizzards and just frighteningly cold temperatures sometimes. I've been outside. I've walked to university in about minus 55, about around minus 60 Celsius, with wind chill, and that was like those are just straight up dangerous temperatures. Like you have to be thoroughly bundled up and like don't be out for long, and preferably don't go outside at all, because it's just hazardous, and in fact. So it was so cold that and there was wind as well, which the wind is the worst part of it all. But like it was so cold that like because of the wind, my eyes were watering because they were dry, because my body's too stupid to not have its eyes water when it's very very cold, and because of that, when I blinked. There would be a little bit of water, just kind of pushed out kind of out to the surface, and it froze my eyelashes together when I blinked. And this is a deeply unsettling feeling, being unable to open your eyes after blinking. So I had to like take my glove and like scrape my eyes. To break up that ice so that I could open my eyes and see where I was going. It was atrocious. It's just stupidly cold. It's like this just isn't fun anymore. Yeah, it was more than a little bit concerning. But yeah, there's definitely been days where once I had to go through the trunk of my car because the door was completely frozen shut. It was impossible to open. So I had to like unlock the trunk and then body check it open and crawl through the back seat to get in at all. It was wild. Yeah, Canadian winters are fairly intense sometimes. Right, I was talking about my flukes and the thunderstorms. So Achilles, our puppy who died a few years ago, and he was an old man. He wasn't a puppy, but he's always my puppy. Yeah, no kidding, right? Heated doors week real nice. He did everything. My goodness. Um, but but yeah, so my pupper Achilles, deathly afraid of thunderstorms. Anytime thunder started, he was glued to your leg. Um, wouldn't leave your side for anything. And so one time, my partner was out of town, and so it was just me and Achilles, and I was heading over to a friend's house that evening to play some board games. And so I was getting ready, and I knew a thunderstorm was coming, but I figured I've got enough time to have a quick shower, and so I hop in the shower, and the thunder just really starts coming in hot, and and so after the first like big peal of thunder, I just because I left the door open to shower because it just gets too steamy otherwise. But I saw Achilles' head poke around the far side of the shower curtain, and he's just like, hey, just checking in, making sure you're okay. Are you scared? Because I'm here. It's all right. You're gonna be okay. And I'm just like, don't, just everything's fine. Just stay out there. And he's like, okay, yeah. Just checking on you. It's fine. I'm fine. Everything's fine. And a few seconds later, a much bigger roll of thunder comes in, and immediately Achilles' head reappears. He's like, "Hey, okay, so just that was big. Are you scared? I'm here for you." And I'm just like, "Please, for the love of God, don't." And he's like, "Yeah, okay, no worries, just making sure." And then a little bit after that, maybe a minute after that, there was just this rattling thunderclap. Like it shook the house. And Achilles was just like, move over, I'm coming in. And sure, just jumps into the shower with me. And I just what do you do at that point? So I'll tell you what I did at that point. My phone wasn't out of reach, and so I got that and took a very carefully framed picture of me and Achilles just hanging out in the shower, and just my proof that this dog has no boundaries of any sort. But yeah, he was a very, very good boy, but very scared of thunder. Absolutely, he was the best. No, Achilles, I think he genuinely felt best about himself when we got some kind of like just simple costumey stuff for my nieces and nephews, and Achilles was living his best life when we put like big butterfly wings on him and a nice feathery boa. I've got a picture of him somewhere in the depths of my phone. Just the biggest smile on his face, with just looking fabulous. Yeah. All right. So very quickly, I'm just gonna do this molecule. And so, looking for electrophilic sites. Again, we're looking for partial positive charges or fully positive charges. And this one's fairly easy. There is a fully positive charge here on that carbon. And so that is a fantastic electrophile. This is in fact a carbocation. And carbocations, so we talked a little bit about this when I was going over SN1 and SN2. Carbocations are extremely good electrophiles because they do not have a full octet, and so these are they just want electrons, and they've got space for them. But also, fashion forward dog, hell yeah, no, he was fabulous. Um, so, kind of similarly to this molecule up here, these hydrogens would also be made quite electrophilic by their proximity to the carbocation, and I'll show you why. Okay, so we'll just have another base coming along. Oh, actually, I also forgot these hydrogens up here would also be electrophilic. And yeah, so just essentially all three of these groups of hydrogen are will have essentially the same properties here, highly similar. So anything that I do here could be applied to any of those hydrogen groups, because they would have the same reactivity. So a base comes in and forms a bond with one of the hydrogens, and because hydrogen can only have one bond at a time, these electrons move down to that carbon. Okay, so that carbon now has a lone pair, and this carbon has a positive charge. So this should look terrible because we have not one but two charges adjacent to each other, and we always try to not have multiple charges because that's kind of terrible. One of my professors would always tell me nature abhors a focused charge, and so if you have two focused charges, that's pretty bad. But this one is not so bad because this lone pair can move down to form a double bond between these two carbons. And when that happens, so we just form a double bond here. And we still got that hydrogen there. And that's it. Now we have got no charges, and all of these carbons have a full octet. So everybody's pretty happy there. And we've gotten to a neutral molecule. We've gotten to a stable molecule. So this is pretty great. And normally, like I would say it would be in fact more correct to octet like in music. Why? Coincidentally, yes. Yeah, those do go together. So I think the more correct way to draw this would be base attacks the hydrogen, and the electrons do not pass go, do not collect $200. They don't stop to make a lone pair. They just go, they bypass that entirely and go straight to forming this double bond. And because this essentially would not form at any point. You would go straight from this product to that one. I only draw this one to kind of illustrate stepwise what's going on, but these do happen simultaneously. Okay. Yeah, and so you could I could have picked any of the 3 hydrogen groups around that carbon and done the same thing. But yeah, so there are all these possible electrophilic sites in this molecule. But yeah, and of course the carbocation itself is the best nucleophile, and you could have words, Nathan. They're important. That carbocation is the best electrophile, and you could have something like, for example, a sodium hydroxide with its negative charge could just come in here and directly attack the carbocation and just attach to this molecule without removing any of the hydrogens. That is absolutely also a possibility here. All right. I'm going to go until about 8:30 tonight. 8:30 my time. It's about another 18 minutes for me. But I would like to talk a little bit about orbitals again. So I said today we're going to get into, let's just go like up here or something. Give myself lots of space. So we had gone over S, P, and D orbitals, and just like how those fit around atoms. So like again with the I'll just draw out here. Let's make it a little bigger. So S orbitals. When we've got we've got our little nucleus here. How shall I draw that? Let's not worry about it. Okay, so S orbitals are just spherical orbitals around the nucleus. P orbitals are the kind of elongated figure 8, and then D orbitals are, except for that weird Z squared orbital that I drew last time, D orbitals are mostly just they take the shape of 2 p orbitals laid at right angles to each other. So these are the atomic orbitals. These are what the orbitals look like when they are around an atom without the influence of other stuff around them. But of course, we like when we do chemistry, we are mixing these orbitals. And when you have a molecule, you have networks of these orbitals that hold the various atoms together. And so we have to address, like, sorry, my jaw's a little sore. So we have to address what happens when we combine these orbitals. And so simplest one that we'll do is, so we've just got 2 hydrogen atoms. So each of these has just 1 electron, and these are in their respective 1s orbitals. So now when we talk about combining orbitals, the method is called linear combination of atomic orbitals. Very good. Okay, so this, you don't really need to remember this part. This is just kind of the method that we use to go from atomic orbitals to molecular orbitals. And I'll leave it there. So when we do this, when we combine two atomic orbitals, or more, because we can definitely do more, but we'll start here. So when we combine atomic orbitals, we always have the same number of molecular orbitals. And what I mean by that is if we are combining two atomic orbitals, like the 1s orbitals of a hydrogen, we're going to end up with two molecular orbitals. So the number of atomic orbitals equals the number of molecular orbitals. That's very important. And it basically what it tells us is that when we combine two 1s orbitals, there's two ways that we can combine them. And we represent them like this. And this is called a molecular orbital diagram. I'm going to write this in a different color because I'm going to be all fancy. So this is a molecular orbital diagram. Okay, so this whole thing is a molecular orbital diagram, and part of the molecular orbital diagram is the I guess depiction of the energy. So these hydrogen 1s orbitals, I've drawn those at the same on the same level, like along the same line, because energy goes from low to high. Come on, like what would be the y-axis, but there's only one axis on this diagram. So these orbitals are equal in energy, and when they interact, so you have two atomic orbitals that combine to form two molecular orbitals, and when they form these molecular orbitals, they're going to have two possible interactions. So there is one of these interactions is lower in energy than the 1s orbitals, and that looks like if we have H over here, and so this is the 1s orbital around the hydrogen. I'm just going to go right there. Okay. So this is one of the hydrogens, and here's the other hydrogen. So this is one possible interaction, and this is this lower energy interaction is when the s orbitals are the same phase. Because when you take two orbitals and they interact and they're the same phase. Remember, I was talking about they combine as if they are just bubbles that are just floating around. They combine each other and they into one bigger bubble, and so another way to depict this a little more accurately is like this. So more or less, this is the shape that this orbital interaction takes. So you can see like it's still like mostly an s orbital, but it combines with the other one, and they flow together, and they so this is what holds these hydrogen atoms together, is this in-phase interaction. And so the other thing about this is that this is called a sigma orbital. So this is sigma, which is just one of the Greek letters. So it's just this little O with a horizontal line out of it. Don't confuse that with when I've done partial charges, I use this symbol. This is a delta. These do not mean the same thing. In molecular orbital diagrams, so sigma bonds, sigma interactions, sorry. Okay, we're going to get through this sentence. We'll do it. I feel it. This is happening. So, in a sigma orbital, which these are, there is electron density along the axis between the hydrogen atoms, and so like if you take a okay, so like taking a model kit, there's these two atoms in the model kit. There's this bond between them, and so these are like if you put them like that, then that bond is on the axis, which is like the shortest straight distance between the two atoms. If there's electron density that overlaps with that bond axis, it's called a sigma bond. And we will get into examples of pi bonds which don't have that, but I just want to get this definition out of the way and then we can move on. So this is no longer an s orbital. An s orbital is now the wrong way to describe this, because the atomic orbitals are the s orbitals, but the molecular orbital here is a sigma orbital. And it is a somewhat useful mnemonic that s orbitals are these spherical. They're spherical around their atoms, and so when two of them come together, they must have some electron density along that bond, because these are just two spheres that are interacting and then elongating like this. So sigma molecular orbitals are formed, can be formed by s orbitals, and so that electron density along this bond remains the same. And so the molecular orbitals also follow the Aufbau principle that we talked about when we were doing atomic orbitals and electron configurations. So the Aufbau rule states that when you are populating orbitals with electrons, you always populate the lowest energy orbitals first. And that applies to this as well. So we started with two atomic orbitals, so we have two molecular orbitals. And in those atomic orbitals, we started with 2 electrons. And so the molecular orbitals must also have 2 electrons. And there they are. They both combine into this lower energy orbital, this in-phase interaction. But the other orbital is also important to consider. It doesn't have any electrons in it, but it's still a thing that exists. So the interaction of these orbitals can either be in phase and lead to a lower energy orbital, molecular orbital, or the atomic orbitals can be out of phase. So this higher energy molecular orbital is this out of phase interaction where the s orbitals around the hydrogens have opposite phase to each other, and this leads to a molecular orbital that would look like this. Okay. So these orbitals now do not combine. Because when I've talked about how orbitals interact, if they're the same phase, they do this. They're like that bubble that comes together into just one bigger bubble. If they are out of phase with each other, then they act like balloons, where you can squish them together and they'll squish and they'll crunch and they'll distort, but they will not overlap like this. They won't combine like that. And so when you have this kind of an interaction, you'll have this node. And a node, just like in atomic orbitals, we talked about nodes in like p orbitals, which are like along there. These nodes are regions, or like a two-dimensional plane, where there is zero electron density. So there's a break in electron density between these two orbitals, and when that happens, so this is, oh gosh, I need to take a second and think. Okay, so I need to back up for just a second and talk a little bit more about this, because this is a sigma molecular orbital because it has electron density along that bond. And because it has that property, because it is an in-phase interaction between these two atoms, it is called a bonding molecular orbital, which I am hereafter going to abbreviate to MO, because that's easier and it's less likely that I'll screw those words up. So this in-phase interaction is a bonding molecular orbital, MO. It holds these atoms together because the molecular orbital is lower in energy than the two separate atomic orbitals. So that is the motivation for these hydrogen atoms to stay together, is because they are lower in energy together than they are apart. Quite the opposite for this out of phase interaction, because this interaction forms an antibonding MO. You can recognize antibonding MOs because along the bond between the atoms, there is this node, this break in electron density, where it switches from, so this would be, there would be a bond along here. So along this bond, it switches from this phase. We'll just call it the negative phase. They're called like negative and positive phases, but it doesn't mean anything except that these phases are opposite to each other. It doesn't mean charge. It has nothing to do with charge. Just there's one phase and then there's its opposite. So when there is a node along a bond, like that intersects a bond, that is called an antibonding MO. And if you fill an antibonding molecular orbital, you break a bond. Because it's like if this had 2 electrons in it, it would break the bond between the hydrogen atoms. And this leads to this like a quite important concept in chemistry called the bond order. And so bond order just refers to like what is the strength of the bonds between two given atoms. And bonding order is so if we abbreviate that, BO equals the I'm just going to call those. So this is electrons in bonding orbitals minus electrons in antibonding orbitals divided by 2. And it's divided by 2 because it takes 2 electrons to form a full bond. So if we look at this example, again, just a neutral hydrogen, just with 1 electron around them, their atomic orbitals will overlap to form these 2 molecular orbitals. By the way, this is called a 1 sigma star. Because this is also a sigma molecular orbital because it has electron density on the bond axis. But the star means that it is antibonding. And again, because it has this node that intersects the bond. Kind of separates them, switches the electron phase. So in this example, we have 2 electrons to work with, and we start with the lowest energy orbital, which is the 1 sigma orbital. It's a bonding orbital, and so this means that there are 2 electrons in bonding orbitals minus 0 electrons in the antibonding orbital. Those are divided by 2, and we should be able to fairly trivially do that math and say that 2 minus 0 divided by 2 is equal to 1. So 2 hydrogen atoms together will have 2 electrons in a bonding orbital, and will have a bond order of 1, which basically translates to there's a single bond between these hydrogen atoms, which is that we've just described H2 or elemental hydrogen or hydrogen gas, or however you want to say that. This is how we describe the kind of bonding situation between them. If there's it's just, this tells us that 2 neutral hydrogen atoms will come together and have a bond order of 1. So they will form a single bond together. Now, let's say I want to take this, see if I can copy it. Ha! Very good. I'm finding out things I can do. Good. Okay, so if we go over here and let's say that one of these hydrogens was H minus. So it's one of the hydrogens is neutral. One of the hydrogens has 1 extra electron. So it has a negative charge. So now, still, both of these hydrogens just have 1 atomic orbital, the 1s orbital. And because they've each got 1 atomic orbital, that means there should still just be 2 molecular orbitals. So 2 atomic orbitals combined to make 2 molecular orbitals, never more, never less. But now we have a different number of electrons that we have to work with. Instead of just having 2 electrons, now we've got 3. So, again, we can only put 2 electrons in each orbital. So the first 2 go into this bonding sigma orbital. But we've got one more. And the only other place we can put it is in the anti-bonding orbital. So now if we do bond order analysis again, so we've got 2 electrons in a bonding orbital, and we've got 1 electron in an anti-bonding orbital. And if we divide that by 2, equals 1 over 2. So if one of the hydrogens started out as like with a negative charge, with an extra electron, now the combination of those hydrogens, it may still make a bond. Like it's not a bond order of 0, which would indicate that they're not bonded to each other at all. But it is a weaker bond. Having a bond order of 1/2 means that there is it's a weaker association than having one bond. So this would be like essentially a half a bond in terms of its strength. Now let's say both of those hydrogens started out negative, and so they both had 2 electrons in their orbitals, and so when they combine, the bonding orbital is filled first, but we also completely fill the anti-bonding orbital. And now, whoops. So we got H and H minus up here, and here we got H minus, H minus. So this one would be 2 electrons in bonding orbitals. I'm just going to call those bonding electrons because I'm lazy. Minus 2 anti-bonding electrons over 2 equals 0 over 2 equals 0. So what this is telling us is that if you have 2 hydrogen atoms that have a negative charge, then they cannot combine. Because if they were to associate at all, the anti-bonding electrons would effectively cancel out the effect of the bonding electrons. And so they would have a bond order of 0, which is to say they have no bond between them at all. So it would just be 2 H minus atoms floating around and never associating with each other. So that's more or less how we combine atomic orbitals into molecular ones. I'm just very quickly going to do this for helium. Just the very next element on the table and the simplest. So neutral helium, which, spoiler alert, you're not going to get helium any other way. But helium has 2 electrons, right? Because it's got 2 protons in its nucleus, and so it has 2 electrons in its neutral state. And so once again, we have 2 atomic orbitals combine to make 2 molecular orbitals, and they'll be exactly the same as the hydrogen ones. Have a 1 sigma for your bonding orbital and a 1 sigma star for your anti-bonding orbital. But helium, just like this case, it has 4 electrons in it, and so we have to fill both of those. And so it'll follow this same equation, except this time we got helium and helium. And so those end up also with a bond order of 0. And this kind of makes sense, because helium, just out on its own in nature, is a monoatomic element, which means that in its kind of natural state, in its state of nothing weird has been done to me, it'll just be one helium atom on its own, just out living life, just being a little guy. And this is the case for all of the noble gases, that they have electron configurations where they have equal numbers of electrons in bonding orbitals to antibonding orbitals, so they don't form bonds with themselves. And for the most part, they don't form bonds with anything, because it just takes an excessive amount of energy. Now, I say in most cases because there are exceptions. But only way down in the periodic table. Like when you get to, I think xenon is maybe krypton, but xenon is the noble gas where you tend to get some chemistry. You can get some with oxygen and fluorine, but that is for an entirely different day. But for most of the noble gases, this is always the case. So helium, we just by looking at the orbitals of helium and applying molecular orbital theory, we could expect that helium will never bond to itself. Like neutral hydrogen forms a diatomic molecule where there's 2 atoms in a molecule. But helium is just a monoatomic element. Does not like to form bonds, and this is why. This is the whole reason that helium does not play well with others, because it's got orbitals that are already full of electrons. It doesn't need or want any more. All right, so that I think is where I'm going to call it for today in terms of talking about new stuff. I fully plan to talk more about molecular orbital theory. Of course, there's tons more to go over. This is, but we have officially scratched the surface of what molecular orbital theory is. And so it's just simple combination of atomic orbitals, and later we'll get into the not so simple combination of atomic orbitals. But this is a pretty good start, and so I just want to say, how's it feeling? How is this like, just does it make at least some kind of sense to you? Also, thank you very much. I do see that. Appreciate it. That is entirely okay. I do not mind at all. But yeah, don't worry about it too much. Like, if you feel like reviewing it, this will be up on YouTube shortly. I think the VODs stay on Twitch for like a week or something. But yeah. So yeah, I'll call it there for the day. But I really appreciate you hanging out, and I hope you have a lovely week. And I will be back here on Friday. All right, you take care and say bye.